Hi, this is Ari Everett for CSC120 Fall of 2023 for Mr. Anderson. This is Ari Everett and definitely not an AI bot that is going through the Lab 13 demo here. So here's the problem statement that we have. We want a pedestrian stoplight, 3 states of go, solid green, don't start, flashing red, and stop, solid red. So we derived and went through the finite state machine design algorithm here with these 5 steps. I'm going to lay this out in more detail on the lab write-up, but here's a very important piece here. The very beginning is the state diagram, which tell us how, on the right here, our chip schematic and our model breadboard here with ICs will allow the information to flow and get our problem statement derived and have a working pedestrian stoplight. So we chose JK flip-flops, we used the transition table, made a next state table, derived a Boolean equations, and simplified as much as possible to create this schematic here. Notice that K1 and K0 have some very familiar formulas here, and we were able to utilize the XOR and XNOR gates in order to simplify the Boolean equations further. So I can't take credit for this. Someone in my group caught this, but it was explained to me that it's good to be able to pick up these patterns in that XOR is either or. You can either have a cheeseburger or a chicken sandwich for dinner, but not either. And then XNOR is all or nothing. You either get dinner or you don't. And you can use these to simplify the K1 and K0 JK input equations down even further. We can see it's all or nothing here. Q and X or Q naught and X naught or Q and X. And the same thing for up over here. So we're able to utilize that and embed it into our board here. So let's go ahead and demo this. Let's start with the chip schematic. So our input is X, as we have in the table here. Let's clear it and run the clock cycle and start at 0. So we're at 0, 0, which is lit up green. Now we want to go to 1 here. I'm looking at the state diagram on the left. We add a 1 and we'll flash off. So input 1, take clear off, run a clock cycle, and we're into off mode here. Let's go into flashing on and off. So that's 0. We have to make sure that X input goes down to 0 and then run this twice, full clock cycle. And we can see it's on here. And we can keep that input at 0 and flash between on and off. So either way, when we add a 1 at the flash on or flash off per the state diagram, it'll bring us to red. So timer as the X input, and we run that clock cycle, and we're into red. Guess what? When we run it again, we're back to green, which is state 0, you can see here, and 0. I'm in poke mode, so let's clear that again. Take this off, take this off. Here we are in green, green 0 here, and 0 here, and that's leave us the green. Now let's move over to our IC modeled, or breadboard modeled IC circuit here. We utilize these chips. I believe this is 7432 for the AND IC, 7486 for the, is it the XOR? Let's see. Yes, it's the XOR. XNOR would have the circle at the front of it. This is the 7404 IC NOT gates, and this is 7408, the AND gates. And our flip-flops, Logisim does not have ICs for this, so we just utilized the block diagrams for them. So similar to our chip schematic, this should run as we have done with the chip schematic. I'll scroll down here. We use these Boolean equations and simplified to run these through the chip schematic, and then use this chip schematic to run it through the proper gates and the ICs. So clear on. Let's run this. Let's clear it. Run the clock a few times. So we're at 0, 0. Green is lit up. Perfect. Let's turn this off. X is to 1. Let's go a cycle. We're off. Let's turn this off and let's flash red. So here we are flashing red. And now let's go to 1 here, whether we're flashing on or off. The next cycle will be turned to red, and we keep that input timer at 1, and it'll bring us back to 0.